The 555 timer consists of a pair of voltage comparators, a flip-flop, and a BJT that acts as a switch. It also has a tray of resistors to set the VTH at 2/3 of VCC and VTL at 1/3 of VCC. The state of the flip-flop is controlled by the comparators as follows. Whenever the voltage of the trigger input drops below VTL, CM comparator 2 fires and sets the flip-flop, forcing Q high and Q bar low. With the low voltage at its base, Q0 is in the cutoff region. The second case is whenever the threshold input rises above VTH, comparator 1 fires and clears the flip-flop, forcing Q low and Q bar high. With the high voltage applied to its base via 100 ohm resistance, Q0 is now heavily on. Summarizingly, lowering the trigger below VTL turns Q0 off and raising the threshold above VTH turns Q0 on. The flip-flop includes a reset input to force Q low and turn Q0 on, regardless of the conditions at the inputs of the comparators. This figure shows the 555 IC configured as an astable multivibrator. Let's say at power turn on, that is at t equal to 0, when the capacitor is still discharged, the voltage at the trigger input is less than VTL. This forces Q high and keeps the BJT in the cutoff region, thus allowing the capacitor to charge towards VCC via the series resistors RA and RB. As soon as the capacitor voltage reaches VTH, comparator 1 fires and forces Q low. This turns on Q0, which then pulls the discharge pin, that is pin 7, to 0 volts. Consequently, C now discharges towards ground via RB. As soon as VC reaches VTL, comparator 2 fires, forcing Q high and turning off Q0. This re-establishes the conditions for a new cycle of astable operation. The time intervals TL and TH can be found by the formulas such as TL equal to RB C ln 2 and TH equal to RA plus RB times C ln 2. The ln 2 factor comes into account from the expression that ln of VCC minus VTH by 2 divided by VCC minus VTH. And plugging VTH as 2/3 of VCC, we get it as ln 2. The frequency is 1.44 by RA plus 2RB times C, and the duty cycle is RA plus RB by RA plus 2RB. As it's shown in the waveform, the capacitor charges towards VCC through the resistance RA plus RB. Once it crosses VTH, the output goes low, forcing Q bar high. Therefore, this forces the transistor into the saturation region. Therefore, the capacitor now discharges towards ground through the resistance RB. And then once again, when it reaches a value below VTL, it once again begins to charge towards VCC and the cycle continues. The initial discrepancy is there because we have to give some time for the 555 timer to set into its stable condition. This figure shows the 555 IC configured for the monostable operation. Under normal conditions, the trigger input is held high and the circuit is in a stable state represented by Q equal to low. Moreover, the BJT switches is closed keeping C discharged or the capacitor voltage equal to 0. The circuit is triggered by lowering the trigger input below VTL. When this is done, the comparator 2 sets the flip-flop, forcing Q high and turning off Q0. This allows the capacitor voltage to charge towards VCC via the resistance R. However, as soon as VC reaches VTH, the upper comparator clears the flip-flop, forcing Q low and turning Q0 on. The capacitance is rapidly discharged and the circuit returns to a stable state preceding the arrival of the trigger pulse. The pulse with T, that is a T on, equal to RC ln of VCC divided by VCC minus VTH. Plugging VTH as 2/3 of VCC, we get T equal to RC ln 3, which roughly translates to 1.1 RC. For further noise immunity, we connect a capacitor between pin 5 and ground. The first waveform represents the trigger input. Initially, the trigger is high at VCC and at some point T it goes low, that is below VTL. When at this point T, the capacitor voltage VC, it starts charging towards VCC. Once it reaches VTH, it immediately discharges to 0 because the BJT which is used as switch is forced into the saturation region. and during this time interval the output q is high, and after this time interval it once again reverts back to its initial state which is low. And in this video we will be using an astable multivibrator designed using the same IC as the trigger input. We will be using a duty cycle of 90%. This is because the 555 IC has a SR latch, SR flip flop, which helps it function as a 555 IC. So the SR flip flop doesn't have a stable state when both the inputs are 1. That is why we use a duty cycle of 90% so that both the inputs are not simultaneously high. Alright, let's design the AC-able multivibrator for the trigger input. Since its duty cycle is 90% and plugging in the standard values of resistors available, RA is 12 kilo ohms and RB is 1.5 kilo ohms. And now using the time period formula, we calculate capacitance as 0.1 microfarad for the input frequency of 1 kilohertz. Now coming back to the monostable circuit, we are using a resistor of value 10 kilo ohms and a capacitor of 0.1 microfarad. This gives us a T-on of 1 millisecond. This is the monostable multivibrator circuit. For the trigger, we have used an astable multivibrator circuit of duty cycle 90%. The circuit has been made according to the circuit diagram, and the standard resistors and capacitors have been used as shown in the design data. The output of the astable multivibrator is given to the trigger input of the monostable multivibrator. Now moving on to the DSO to check the waveform. Yeah, this is it. The yellow waveform is of the astable multivibrator's output. The green waveform shows the output of the monostable multivibrator. Just as we designed it, the frequency of the astable multivibrator's output is around 1 kHz and the plus duty cycle is around 88%. As you can see, we have used a resistor of value 10 kilo ohm and a capacitor of value 0.1 microfarad. The T-on period designed is around 1 milliseconds. Now, when you are going to check the DSO, you can see that the T-on period is around 720 microseconds, which is 0.72 milliseconds. Now, checking the capacitor voltage across pin 7. Now stopping the waveform, you can see that the capacitor charges from 0 to VTH when negative pulse is encountered and immediately discharges after the T-on period is over. Once again, the cycle continues when the next negative pulse is encountered. Now matching the two waveforms like this, now it's pretty clear that what I said is right. When a negative pulse is encountered, it charges to VTH and then discharges immediately after the T-on period is over, and then this cycle continues in the next negative pulse also. That's it.